So this is part 2 of our solubility series, and this type of problem we start with the KSP and the formula of the salt, and we calculate the solubility using a rice table. And then once we have molarity, we'll determine grams per liter. So here's our problem for copper 2 iodate. The stoichiometry obviously is the copper iodate. We get 1 copper ion and 2 iodates. Therefore, the mass action equation, the solubility product, is the copper times the iodate squared. Now the iodate has got to be twice the copper if we look at the balanced equation. So for the iodate we put in 2 times the copper 2 plus. That then gets squared, and we combine like terms. We get 4 times the copper ion cubed is equal to the KSP. We know the KSP, 1.4 times 10 to the negative 7th. And so we divide by the 4, and we get the cube of the copper, 35 times 10 to the negative 9th, which means the copper concentration is 3.3 times 10 to the negative 3rd, and the iodate is twice that. All right. Now, the next type of problem you will see is called the common ion effect problem. And these are very interesting. So what is the solubility of calcium hydroxide? Fine, easy enough if we know the KSP. But how about if it's in 0.1 molar calcium nitrate? Now, the calcium nitrate is completely soluble because all nitrates are highly soluble. And so the calcium ions that start off in the solution are 0.1 molar. So what that means is, if you look at the balanced chemical equation, the fact that we've got a very high concentration of calcium to begin with means that we might expect that the calcium hydroxide would be more or less soluble. And I think you'll see that if we pump this up, to keep the solubility product the same, we've got to reduce the amount of hydroxide in solution. So we set up our ice table here with the solubility equal to the calcium ion concentration, but only the calcium from the calcium hydroxide solid that's dissolving. So here's our ice table. We start off with no calcium hydroxide solid. We've got some, but it's a 0 concentration because it's meaningless. The calcium's 0.1 and the hydroxide is 0. Now, the system comes to new equilibrium as we get a little bit of the calcium hydroxide to dissolve, but the KSP has to be the same. All right. Well, is the calcium from the calcium nitrate going to go down or up much? Well, we've got a pretty small solubility of the calcium hydroxide. So I'm going to guess and assume that the calcium in equilibrium is still 0.1 molar. And we'll call the small amount that dissolves X. Now, the calcium that dissolves X is going to increase by X, the 0.1 molar. The hydroxide, 2-hydroxide, is going to also be X. Now, X is quite small compared to 0.1, so we can simplify this, treating it as negligible, treating it as 0. And the equilibrium concentration of calcium then is 0.1. When we then solve this equation with calcium as 0.1, we will divide both sides by 0.1, and we will then take the square root, and we get the X equal to 8.05 times 10 to the negative 3rd. That's the amount of new calcium that we've got, which compared to 0.1 is negligible. The solubility of the calcium hydroxide itself is half that, because we're solving for X. I hope that's clear. Was our assumption of X being negligible or reasonable one? Yes, it was. Because this is 0.00805, and we've only got 2 significant digits here, so it's not going to move the 0.1 on the calcium at all. This is what common ion effects do. They will reduce the solubility less than the in pure water. Now, the general rule is the negligible is negligible if it's less than 5% of the equilibrium value of what you're solving for, and it is. Next, predicting the effect of pH on solubility. You got to think about what you know about acid-base and the Bronsted-Lowry definition of acids and bases. And we can see, will hydrogen ion addition from a strong acid affect the solubility of a salt? We're going to study lead bromide, copper 2 hydroxide, and iron 2 sulfide. And you need to remember what the strong acids are. And they are all the hydrogen halides except HF. So HCl, HBr, and HI are strong acids. Then you've got sulfuric and nitric and perchloric acid. Okay, if you memorize those, you've got a good start. So we have to write a balanced dissociation equation, which you've already done, for the salt. And note what the anion is. If it's a weak acid ion, it reacts with a hydrogen ion and shifts the equilibrium position towards more dissolution. But strong acid ions, anions, do not react. So the chloride, the bromide, the iodide, the sulfate, and so forth. So if you've got a strong acid ion, added hydrogen ions have no effect. And when you study Le Chatelier's principle, you'll see that this is a good way to use Le Chatelier to predict qualitatively what happens. So here we are. Lead bromide dissociates into lead and 2 bromides in water. Now the addition of hydrogen ions does not form a weak acid with bromide. Therefore, it's not going to take any of the bromide out. Hydrogen ions and bromide ions, they like hate each other. The low energy position and high entropy position is for them to be separated by the water molecules. So nothing happens. You just ignore the strong acid concentrations. Let's look at the copper hydroxide. It's interesting. We know that adding hydrogen ions will do something. It'll make water, won't it? And that pulls water out, and at least by Le Chatelier's principle, we'll say that that would mean more hydroxide, more copper hydroxide is going to dissolve. It's kind of like the hydrogen ions are reacting with the copper 2 hydroxide, pulling the hydroxide ions away to make water. So yes, with these transition metal hydroxides, yes, there will be a definite reaction, and you'll increase, by adding acid, you'll increase the solubility. Now let's look here. With iron 2 sulfide and water, you have the iron, of course, but you also have the hydrogen sulfide ion and the hydroxide ion. Now, if you add acid to this, it'll react with the hydroxide, yes. If you get water, it'll also react with the HS- to make hydrogen sulfide, which is poisonous gas. Stay away from that. So, yes, acid, adding acid, strong acid, will take the hydroxide out and force more copper hydroxide to dissolve. And here, both the hydroxide and the hydrogen sulfide ions will react with the hydrogen ions. And that means that more of the iron sulfide than we would expect with just water will dissolve in the acid. Next type of problem, the one we see frequently on undergraduate tests, is predicting whether a precipitate will form if we know the KSP. So we ask, does a precipitate form when 0.1 liters of 0.3 molar calcium nitrate is mixed with 0.2 liters of 0.060 molar sodium fluoride? Now you first have to see, is there any precipitation possible, or are we just forming very soluble salts? Well, and the answer here is, remember, fluoride, unlike the other halides, when you're going to react it with a lot of metals, it's not going to be very soluble. So, although sodium nitrate, the crisscross there, is certainly highly soluble, calcium fluoride is not. So you decide that. Then you look up the KSP for the substance, and from the initial concentrations after mixing, you calculate Q, that is, the mass action expression, but using the initial concentrations. If you compare it with KSP and Q is greater than KSP, a precipitate will form. So here's a look at this one. First, the calcium ion concentration, moles of calcium ion divided by the total volume. So we know the total volume now is 0.2 liters because we mixed the two together. So we've got 0.3 molar times 0.1 liters divided by 0.1 liter plus 0.2 liters. And the moles of fluoride added divided by the total volume here, 0.06 times 0.2 divided by, again, the same volume, 0.3 liters. If we substitute into the ion product expression, Q is the calcium times the square of the fluoride. We've got 0.1 times 0.04 squared. I just wrote it out like this. When we multiply those together, we get 1.6 times 10 to the negative fourth. That's Q for the solubility product. But KSP is 5.3 times 10 to the negative ninth. This is way bigger than the KSP, so a precipitate will form. This is how you do these problems. You need to figure out the molarity of the two ions once they're mixed, and then see if Q is greater than KSP, in which case it does form a precipitate.